Çevremler akım.
Okay, so ne oldu? Buradan önce sen. Ya bunu verecek vermeyecek Allah bilir. Onda işiniz yok. Koy orada olsun. Karıştırmayın yok ha. İşte oradan eleyersiniz. Ha. Oldu. Hayır. Next speaker is Dr. Aygun Mammadova from Institute of Physics, Ministry of Science and Education of Azerbaijan Republic. Title of talk is Confined Position Dependent Mass Harmonic Oscillator as a Model for an Abrupt Semiconductor Heterojunction. So please.
Thank you. We study confinement quantum systems, and as is known, quantum confinement is a phenomenon where a particle's movement is restricted in one or more dimensions by nanoscale structures, leading to discrete energy levels and modified electronic and optical properties. These confined systems, such as quantum dots, quantum wells, and quantum wires, have unique electronic and optical properties due to the confinement of electrons or holes in one or more spatial electronic and optical properties due to the confinement of electrons or holes in one or more spatial dimensions. It's known that in bulk materials, electronic or optical properties do not depend on the size of the material, and the energy graph of these materials is smooth, and optical and electrical characteristics can be described by the laws of classical mechanics. But when the size of these materials are reduced to nanoscale, for example, 5 and 10 nanometers, 5 or 10 nanometers, then the process occurring in these materials can only be described by the laws of quantum mechanics. By reducing the size of these semiconductors, we obtain quantum wells, 2D materials, quantum wires, 1D materials, and quantum dots, 0D materials. The dose is a density of electron states. In these materials are modified due to quantum confinement. In bulk materials, the density of electron states is continuous and proportional to the square root of energy, square root of energy. Low-dimensional structures such as quantum wells, quantum wires, and quantum dots exhibit a modified dose due to quantum confinement. Quantum wells are thin layers of a semiconductor materials sandwiched between two layers of a wider bandgap material. The confinement in one dimension leads to the quantization of energy levels and the formation of discrete subbands. Quantum dots are zero-dimensional nanostructures with confinement in all three dimensions. And in quantum dots, consist of discrete delta function like peak at the energy levels, and strong electron hole interactions. In quantum wells, particles are confined in one dimension, but are free to move in two dimensions. About the electronic properties, we can say that instead of a continuous band of energies, carriers can only occupy discrete energy levels called energy subbands within the confined dimensions. This creates 2D electronic systems with properties between bulk materials and molecular. In quantum wires, particles are confined in two dimensions, but are free to move along the third dimension. There are quasi-1D systems, a type of nanostructure used in electronics to efficiently transport electrons. C is quantum dots. In quantum dots, particles are confined in all three dimensions. Energy level become completely discrete, and the density of states is zero outside these discrete energies. This confinement results in size-dependent energy bands and densities of states with smaller structures exhibiting larger band gap and more discrete energy levels. Next one. Quantum wells currently focus on intensive theoretical and experimental research because of their wide range of applications. In the devices based on 1D gallium arsenide, aluminium gallium arsenide, N-type heterostructures, quantization effects become stronger as the subband spacing increases due to the decreased electron effective mass. One of such research works is the article Self-Consistent Analysis for Optimization of Aluminium Gallium Arsenide based heterostructure, published in Journal of Electrical Engineering and Technology of the Korean Institute of Electrical Engineers. The wafer is built on aluminium gallium arsenide heterostructure with modulation doping using molecular beam epitaxy Reiber 32 system. An abrupt aluminium gallium arsenide heterojunction is a semiconductor interface where gallium arsenide is directly joined with aluminium gallium arsenide over a very short distance, ideally on the atomic scale. Unlike graded interfaces, an abrupt junction features an immediate change in material composition, creating a sharp band gap difference that's crucial for application like aluminium gallium arsenide, HBT, heterojunction bipolar transistors, and quantum well devices. The high degree of abruptness is achieved through precise growth techniques such as molecular beam epitaxy or metal-organic chemical vapor deposition. Second figure, a coaxial structure is formed from a one-dimensional material. The conduction and valence band are disrupted by the interaction of atomic and nuclear electrons. In this work, aluminium gallium arsenide based one-dimensional tetrastructure and its interface using self-consistent coupling mechanism have been discussed. The charge carriers were induced by the conduction and profile and the electronic potential. The electronic structure of such low-dimensional systems is determined by solving the Schrödinger equation with appropriate energy operator and boundary conditions. To choose the kinetic energy operator of the heterojunction, it's necessary to take into account the position-dependent effective mass and the sharpness of the interface. Here, the confinement potential V equals m omega squared, omega 0 squared x squared by 2 leads to the quantization of energy levels and the formation of discrete states. The wave functions of the confinement states are localized within the nanostructure and have a specific spatial distribution. In this equation, mass depends on position, because in heterostructures, the effective mass of electrons changes across the interface due to changes in the semiconductor materials. In a quantum well, especially a heterostructure, the effective mass of a charge carries is not uniform. It changes with position, particularly near the interface between different semiconductor materials due to the variation in material composition and band structure. The position-dependent mass approximation is widely used in semiconductors and heterojunction because electron and holes in these materials don't behave like free particles with a fixed mass. Instead, the effective mass depends on the local environment, such as material composition, strain, and band structure. By applying this approximation, the effective mass is included in the Schrödinger equation, allowing more accurate calculation of electronic and optical properties such as subband energies and optical absorption, which are crucial for designing and controlling semiconductor devices such as quantum wells and quantum dots. Next one. A specific form of the effective mass Hamiltonian for semiconductors with position-dependent mass at abrupt heterojunction is Drucker-Krinemer operator, characterized by its specific operator ordering parameters A equals -1/2 and B equals 0. This operator ensures the Hamiltonian is Hermitian and provides the correct boundary condition for wave functions and their derivatives across abrupt junctions, which are crucial for accurately modeling phenomena like electron transmission and tunneling in these structures. This generalized Hamiltonian has this form, and Vx is potential energy. So our potential energy is m omega squared x squared divided by 2, like harmonic oscillator, in the negative a and a values, and will be infinitive in x equals to plus minus a. Next one. Exactly solving second order differential equation, we obtain the following non-equidistant energy spectrum for the Drucker-Krinemer model of a non-relativistic linear harmonic oscillator. And the following expression for the wave function of stationary states. Here, Cn lambda x is Gegenbauer polynomials, and Cn Drucker-Krinemer is the normalization coefficient defined as the follows. Next. In this figure, depicted confined quantum harmonic oscillator potential and behavior of the non-equidistant energy levels and probability densities of the ground and excited states. First one excited state for value of the confinement parameter A equals 0.5. Next for confinement parameter 1. And the next one is A equals 1.2. And next for stage of A equals 2. And here m omega and the h bar equals to 1. The following figure shows the dependence of energy levels of the confinement parameter A for the ground and 10 excited states. From energy spectrum, we observe that the reduced frequency of the non-linear energy spectrum found by exactly solving the Schrödinger equation expressed by the Drucker-Krinemer kinetic energy operator for the model of harmonic oscillator top infinite deep quantum wells. Depends on the confinement parameter and increases sharply when this parameter approaches 0. This case differs from other non-confined oscillator models and explains sharp dependence of energy spectrum from confinement parameter A for a much less than 1. Quantum wells, wires, and dots are real-world realization of dimensional reduction and boundary-determined physics. While they exist in condensed matter, their structure and behavior parallel the ideas behind the holographic principle. that lower dimensional surface or boundary can encode the full physical reality of a higher dimensional system. Next. Thank you for your attention.
Is there any questions?
Yes, I have
Oh.
questions. Aygun, thank you for your presentation and speech. I have a question. How do you think which quantum confined systems is most promising for future technologies?
Quantum wheels, quantum wires, and quantum dots, they are all very useful for us and for future. But quantum dots, we know that they use in technology, nanotechnology, in our, for example, televisions and other devices.
Yes.
And that's why this works is crucial for our
Yeah, yeah.
future technology.
It's interesting results. Nowadays, the researchers use the quantum dots and the experimental for the semiconductor materials and the late. And do you check these results in the experimentals or compare the experimental results?
Yes, there are some results from experiments too, and we check them, but our results are general, but they use value results, and that's why we can check only some values from the experiment results.
Thank you. It's so interesting for me. Thank you.
Thank you.
Let's thank speaker again. So